In this tutorial, we're going to use a free body diagram to calculate some forces. The scenario is one that we encountered in a previous video, namely people pulling a piano up a ramp using a rope, and I'm going to assume that you already understand how to draw the free body diagram on the right. If that is not the case, you should go back and view the previous video on drawing free body diagrams. In this case, we're actually going to use this diagram to calculate the tension and normal forces acting on the piano. A lot of the text information on screen is already encompassed in the free body diagram, so I'm actually going to erase a lot of this so we have more room. And let's just list the essential details. So we know that the piano is moving at constant speed up the ramp. We'll use that. We're also told that the mass of the piano is 136 kilograms. Okay? In general, the magnitude of the weight force is just mass times little g. So in this case, it's the mass of the piano times little g. That will be the magnitude of the weight force. And our first goal should be to decompose that weight force into x and y components as shown on the free body diagram. Let's first consider the wx vector shown there near the bottom. Well, its magnitude must be the magnitude of the overall weight vector, w, times the sine of 27 degrees. But we also notice that it's pointed in the minus x direction, namely the negative I hat direction, so wx should be minus the magnitude of w times the sine of 27 degrees times I hat. You can go through the same logic for wy. This is the magnitude times cosine of 27 times j hat. Both of those vectors are negative, and you can clearly see that on the free body diagram. Now that we've decomposed it, we can go through, gray out the overall weight, we don't want to double count, and just have wx and wy. So we have our four forces acting on the piano. We're going to need a little room to do calculation, so I'm actually going to shrink down the free body diagram, put it over here on the side. And so now what do we do to figure out the tension and normal forces? Well, you'll note that the piano is moving at constant speed. That's very important, because that tells us that the net force on the piano must be zero. This statement can be broken down into both x and y statements, noting that the sum of all forces in the x direction must be zero. That Greek letter sigma just means the sum of. And it's also true that the sum of all the forces in the y direction must independently be zero. Okay, that should help us figure out what the tension and normal forces are. Let me show you. Let's start with the x statement. The sum of the forces in the x direction is zero. Well, looking at the free body diagram, you can see there are two forces in the x direction, wx and the tension. So it must be the case that 0 equals the vector sum of the tension plus wx. This can be easily solved for the tension force, which is just negative wx. And conveniently, we have an expression for wx over there on the left. So the tension must equal negative that expression. So the two negatives are going to cancel out, meaning the tension will be the magnitude of the weight times the sine of 27 degrees I hat. But we know that the magnitude of the weight is just the mass of the piano times little g, so we'll plug that in. Now we can put in numbers. The mass of the piano is 136 kilograms. We put in 9.8 meters per second squared for little g, sine of 27 times I hat, calculate all that, and we find that the tension force is 605 newtons times I hat, where I wrote out the word Newton just so you don't confuse it with normal force. Alright, that's the tension. That means that the rope is exerting that force on the piano in the positive x direction. Let's record that over on the left. Next step is to figure out the normal force acting on the piano. So the normal force is exerted by the ramp on the piano. And we can use the same sort of strategy except now in the y direction. So the sum of all forces in the y direction must be zero. According to the free body diagram, there are only two forces in the y direction, so 0 must be the vector sum of the normal force n plus the weight in the y direction wy. That means that the normal force itself is negative wy, and again we have an expression over on the left for wy. The negatives cancel again. We put in mp, g, and the cosine of 27 degrees. We see that the normal force comes out to be 1.19 times 10 to the third newtons times j hat. So let's record that value over to the left as well. Now before we officially declare this problem solved, we should make sure that the numerical answers we just got are consistent with our diagram. Make sure we didn't screw up the signs. So the tension points in the positive x direction on the diagram, and indeed we have a positive number times I hat, so that checks out. Normal force points in positive y. Our expression is a positive number times j hat. That checks out. Intuitively, it also makes sense that the normal force is bigger than the tension force. The ramp is angled at 27 degrees, so you can imagine in that case, the ramp is actually supporting more of the piano's weight than the people. That wouldn't be the case if the ramp were inclined to 80 degrees or 85. That's a ridiculous ramp. But at that point, you can imagine the people would really be supporting most of the piano's weight, and the ramp would be contributing only a little bit. For a 27-degree ramp, though, you would expect the normal force to be bigger in magnitude than the tension force, and indeed that is the case here. Everything checks out, looks like those are our forces.